Welcome back to The Explainer. Today we're diving into a hidden technology that is quietly, but absolutely, powering our modern world. We're talking, of course, about printed circuit boards or PCBs. They're really the invisible infrastructure making virtually every piece of tech you rely on possible. From the device you're using to watch this right now, all the way up to the satellites orbiting above us, PCBs are absolutely the silent workhorses of the modern age.
But before we get too deep into the weeds, I want you to just take a quick look around. Seriously, mentally inventory your immediate surroundings for a second and ask yourself, how many PCBs are actually in the room with you right now? Because, well, if you just counted your laptop or your phone, you're drastically underestimating. Your smart light bulb? It's got one. Your electric toothbrush? Yep, that too. Honestly, if something plugs in, lights up, or communicates, there's almost certainly a PCB hidden inside of it.
Okay, let's dive into this. Just think about the mind-blowing volume of everyday items relying on these boards. Your smartphone uses them for processing and wireless communication. That Wi-Fi router just sitting on your shelf, it's using a PCB for complex networking. Even your air conditioner relies on them just to control the temperature. From your smartwatch, to the wall charger converting your power, to your television processing high-def audio and video, literally every single one of these functions is made possible by a specialized printed circuit board.
So, let's start with Section 1, the foundation of electronics.
At its very core, a PCB provides the organized electrical and mechanical platform that allows all these different electronic functions to actually work together seamlessly. You can kind of think of it like the central nervous system of an electronic product. Just like your own nervous system connects your brain to your muscles and senses, a PCB physically and electrically connects processors, memory chips, sensors, and power supplies so they can all communicate instantly.
Whenever an electronic product needs to perform a task, it's relying on this nervous system. And the core functions? They're vast. Whether a device needs to receive and regulate power, process some complex information, sense environmental data like, say, temperature or motion, or just communicate with a wireless network, a PCB is basically pulling the strings. It's what allows a system to physically drive a motor, store your data, or light up a display. It is the ultimate integrator.
Now here's a really common misconception we need to clear up right away. People often think one product means one board, but actually one complex product rarely contains just one board. Take a modern vehicle, for instance. It doesn't just have a single car computer, it contains dozens of electronic control modules. You've got separate boards for the engine, the lighting, the infotainment system, battery management, airbags, you name it. Even your laptop contains several specialized boards, like your main motherboard, a separate display board, and a charging circuit, all working together.
Which brings us to Section 2, Everyday Consumer Tech.
Consumer electronics is undeniably one of the largest areas of PCB use globally. But designing for this space is incredibly demanding in a very specific way. Designers making consumer tech have to focus heavily on miniaturization and low power consumption. They have to keep things tiny and highly energy efficient. But just as importantly, these boards must have a low production cost and be super easy to push through high-volume manufacturing. I mean, when you're making tens of millions of smartphones, the packaging has to be ultra-compact, and literally every fraction of a cent in production cost matters.
Now, what's really interesting here is how consumer demands have literally changed the physical shape of the technology. We aren't just dealing with rigid, flat boards anymore. Flexible PCB technology has become absolutely essential for wearable electronics. Think fitness trackers, smart glasses, or your smartwatch. Because these devices have to fit into curved, extremely compact, and comfortable spaces right against the human body, the PCB itself actually has to bend and flex without breaking. Pretty cool, right?
Let's shift gears and look at the extreme frontiers. Section 3, high-stakes reliability.
And this brilliantly illustrates the massive divide in engineering requirements depending on a product's final purpose. Take a look at a children's electronic toy. The priorities there? A simple circuit, low cost, and high-volume production. If it breaks, well, it's just a bit inconvenient. But compare that to an aircraft flight controller. The priorities completely flip to extreme reliability, strict weight limits, and massive environmental resistance. They're both PCBs, sure, but the engineering approach is just worlds apart.
For industries like automotive and aerospace, the operating environments are incredibly harsh. Just think about what a PCB inside a car engine bay or a spacecraft goes through. These boards demand high reliability and a massive operational life. They have to resist constant, violent vibrations and tolerate extremes ranging from the freezing cold of space to boiling engine heat, not to mention extreme moisture resistance. A standard television PCB would literally vibrate to pieces or just melt in those conditions. And because of these brutal environments, the consequences of a high-reliability failure can be totally catastrophic. If an airbag sensor board fails or a drone's flight controller glitches midair, lives are on the line. That's exactly why the entire manufacturing approach fundamentally changes for these sectors. It demands significantly stronger engineering control, super strict multi-layered inspections, and rigorous documentation to trace every single component right back to its origin.
This high-stakes reality is incredibly prominent in medical electronics too. Whether we're talking about a blood pressure monitor, an MRI machine, or a wearable health monitor, medical boards prioritize absolute electrical safety and precision. Take signal quality as an example. An ECG machine relies on a PCB to receive incredibly weak electrical signals from the human body, amplify them, and filter out all the electrical noise so doctors can actually read your heart rhythm accurately. The strict regulatory inspection required here is just beyond intense.
Moving on to Section 4, Connecting the Physical World. Let's move to this next concept and see how it builds on everything we've talked about. In the world of the Internet of Things and embedded systems, everything runs on an elegant four-step feedback loop: sense, process, communicate, act. So for example, a PCB might first sense the soil moisture in a smart agriculture setup. Then, the onboard processor processes that reading. Next, it communicates via Wi-Fi to a cloud server. And finally, it acts by triggering a water pump. The PCB is the physical stage where all four of these critical steps interact.
You see the same feedback loop operating on a massive scale in industrial automation and robotics. Factory lines and mobile robots have to operate continuously without breaking down. These industrial boards require incredible resistance to electrical noise from heavy machinery. They combine sensors, motor controllers, and processors all into one unit. But most importantly, a custom PCB enables a factory or a robot to take what would otherwise be a giant, messy web of fragile wires and condense it down into a compact, robust, and highly reliable integrated board.
To really put this into perspective, look at the staggering industry application map. Over in human life, we have medical and wearable tech. In mobility, it's electric vehicles, standard automotive, and aerospace. Industry relies on them for automation and robotics. Communication depends on them for global telecom and networking. And in energy, PCBs are out there managing solar arrays, battery storage, and complex power electronics. Across all these completely diverse domains, the PCB acts as the foundational, unifying platform.
Finally, we arrive at Section 5, the Golden Rule.
So, the crucial point is this. If you take away only one thing from this explainer, let it be this golden rule. The application determines the PCB requirements. A PCB does not have one universal, one-size-fits-all purpose. The environment, the electrical function, and the required reliability level of the final product dictate literally every single engineering decision made during its design. A smartwatch board and a satellite board share the same basic concept, sure, but the final application makes their execution entirely different.
And this means that designing a PCB is never an isolated task. PCB design is, in fact, product engineering. A board rarely works alone. It has to perfectly integrate with the mechanical enclosure wrapping around it, the specific power source feeding it, the complex software running on it, and the physical sensors connected to it. Basically, it's the physical platform that enables modern electronic intelligence to actually interact with the real world.
And that brings us to the end. But before I let you go, I want to leave you with a thought-provoking question to chew on. Which industry would be most affected if PCB technology just disappeared tomorrow? Honestly, there really isn't a single correct answer, because as we've seen today, our entire modern society, from the phones right in our pockets to the planes in the sky and the medical monitors keeping us safe, relies absolutely on this invisible infrastructure. Thanks so much for joining me on this deep dive, and I'll catch you in the next explainer.